Welcome to vsrtechinfo. This is VS Rao. In this video, we will look at ultrasonic sensors for Arduino. In this, we will see the model HC-SR04T and another model JSN-SR04T. HC-SR04 is the basic model, which is open-ended ultrasonic sensor. JSN-SR04T is a waterproof sensor. Note here, the sensor and the cable are waterproof, not the circuit board. We will see the comparison between these two models and also how to use them along with Arduino with the code. Let us go into the details now. How ultrasonic sensors work. Ultrasonic sensors work by emitting sound waves with a frequency that is too high for a human to hear. These sound waves travel through the air with a speed of sound roughly 343 meters per second. If there is an object in front of the sensor, the sound waves get reflected back and the receiver of the ultrasonic sensor detects them. By measuring how much time elapsed between sending and receiving the sound waves, the distance between the sensor and the object can be calculated. This is the basic concept of ultrasonic sensors. Bats, whales use them while measuring the distance during their traveling. At 20 degrees centigrade, the speed of sound is roughly 343 meters per second or 0.034 centimeters per microsecond. If you multiply the speed of sound by the time the sound waves traveled, you get the distance that the sound waves traveled. Distance equal to speed into time. But that is not the result we are looking for. The distance between the sensor and the object is actually only half this distance, because the sound waves traveled from the sensor to the object and back from the object to the sensor. You can see in the diagram, the transmitter is emitting the sound waves which reaches the object, and the reflected sound waves will come back to the receiver. So this is the distance, and the actual distance for measurement is half of this distance. So you need to divide the result by 2. Distance in centimeter equal to speed of sound centimeter by microsecond into time microsecond divided by 2. Temperature dependence of speed of sound. The speed of sound actually depends strongly on temperature and to a far lesser degree on the humidity of the air. For most of the cases at 20 degrees centigrade, you can just use 343 meters per second, but if you want to get more accurate readings, you can calculate the speed of sound with the following formula. V meters per second equal to 331.3 plus 0.606 into T, where V is the speed of sound in meters per second and T is the air temperature in degrees centigrade. This formula does not include the humidity since its effect on the speed of sound is negligible. Specially adapted ultrasonic sensors can also be used underwater. The speed of sound in water is 4.3 times fast than in air, so the calculation must be adjusted significantly. While some sensors use a separate sound emitter and receiver, it's also possible to combine these into one package device, having an ultrasonic element alternating between transmitting and receiving signals. The image here shows separate transmitter and receiver in HC-SR04 model, wherein JSN-SR04 model has got only a single device which will be alternating between both transmitting and receiving of the sound waves. Ultrasonic sensor uses. Ultrasonic sensors find its way in robot navigation as well as factory automation. Water level sensing is another good use and can be accomplished by positioning one sensor above a water surface. The image here shows the sensor mounted on top of the water tank to measure the water level. If configured correctly, ultrasonic sensors can even measure fluid flow rates. Since sound is traveling through a moving medium, the speed of sound relative to these elements will be increased or decreased by the velocity of the fluid. How HC-SR04 ultrasound sensor works. At the front of the HC-SR04 sensor, you can find two silver cylinders, that is ultrasonic transducers. One is the transmitter marked as T of the sound waves and the other is the receiver marked as R. To make the sensor generate a sonic burst, you need to set the trigger pin, which is marked as TRIG, to high for at least 10 microseconds. The sensor then creates an 8 cycle burst of ultrasound at 40 kHz. The image here shown, the trigger pin when a voltage is made high for 10 microseconds duration, the pulses of 8 cycle burst are formed. This sonic burst of 8 pulses travels at the speed of sound and bounces back and gets received by the receiver of the sensor. This is received in echo pin. Here 10 microsecond pulse is applied as a trigger and 8 40 kHz pulses are transmitted as a burst, and when they receive the bounce back, the echo pin produces the pulse and the time duration is nothing but the distance between the sender and receiver, that is transmitter and the receiver. The echo pin then outputs the time that the sound waves traveled in microseconds. You can use the pulseln function in the Arduino code to read the length of the pulse from the echo pin. After reading echo, you can use the formula to calculate the distance between the sensor and the object. Distance centimeters equal to speed of sound centimeters by microseconds into time microseconds divided by 2. HC-SR04 specifications. The operating voltage of this HC-SR04 is 5 volts and the operating current is 15 milliamperes. Frequency of operation is 40 kHz. The measuring range is 2 to 400 centimeters. Resolution is 3 mm. Measuring angle is 15 degrees. Trigger input signal is 10 microseconds high pulse. Echo output signal is input TTL level signal at the range in proportion. Dimension is 45 by 20 by 15 mm. HC-SR04 connections with Arduino. on the Arduino side, the 5 volts is connected to HC-SR04 VCC. Pin 2 on Arduino is connected to trigger, and pin 3 on Arduino is connected to echo. Ground on Arduino is connected to ground of HC-SR04. Note here, pin 2 and pin 3 you can change to any other pins as per your choice. This is the complete wiring diagram of HC-SR04 ultrasonic transducer connected to Arduino using the breadboard. Example code for HC-SR04 with Arduino. After wiring the ultrasound sensor with Arduino Uno, it is time to connect the Arduino to the computer and upload some code using the Arduino IDE. The example code is shown here. This example code uses no library, that is, library function is not required. The first 2 lines define trigger and echo pins. Here pin number 2 and pin number 3 are used, and pin number 2 is trigger pin and pin number 3 is echo pin. Next, variable definitions. Duration is defined as long and distance is defined as integer, that is declarations. Now in setup, that is void setup, define inputs and outputs. Pin mode, the trigger pin and echo pin are defined here. Trigger pin is defined as output pin and echo pin as input. Then serial begin 9600. This is serial communication at a baud rate of 9600. Then comes void loop. Under the loop, clear the trigger pin by setting it low. This initially is required to avoid any false reading. Digital write trigger pin is set as low and a delay of 5 microseconds is kept here. Then trigger the sensor by setting the trigger pin high for 10 microseconds. This is to apply the trigger pulse to the ultrasound sensor. Digital write trigger pin is made high and the duration is set to 10 microseconds via the command delay. Then the trigger pin is made low. Now next, reading the echo pin using pulseln function. Return the duration. This pulseln function returns the duration, that is length of the pulse in microseconds. Duration is a variable which stores the length of the pulse. Pulseln function with echo pin comma high. Calculate the distance. Duration into 0.034 by 2. This gives the distance, and that is stored in the distance variable. Now next, print the distance on the serial monitor. You need to use Control plus Shift plus M to see the output on the serial monitor. Serial.print distance equal to, this line prints on the serial monitor distance equal to. Serial.print distance. This distance is nothing but the variable output or the variable contents are printed here. Then serial.println CM. This is the last line. Example, distance equal to the value and in CMs. will be the output of the monitor. Then a delay of 50 is incorporated in the program, and this goes on in the loop. Now next, example code for HC-SR04 with Arduino and New Ping library. Here in this code, we will be using the library function. The NewPing library can be used with many ultrasonic distance sensors. You can install the library by going to Sketch, Include Library, Add .zip library in the Arduino IDE. The code which uses the NewPing library is a much shorter than the code used earlier. Besides that, the NewPing library does include some other nice features. It allows you to set a maximum distance to read. It won't lag for a full second when no echo is received, and it has a built-in median filter. The library includes some examples that you can use, but you will have to modify them to match your hardware setup. Here is a modified example code that can be used with the same wiring setup as before. HC-SR04 Ultrasonic Distance Sensor with NewPing library example code is shown below. Include the library, that is, include newping.h. Define pins and maximum distance. Here hash define trigger pin, which is 2, and hash define echo pin is 3, and hash define maximum distance is 350. Maximum distance we want to ping for in centimeters. Maximum sensor distance is rated at 400 to 500 centimeters. New ping sonar, trigger pin, echo pin, maximum underscore distance. This is new ping setup of pins and maximum distance. And the duration and distance are declared as float variables. Void setup. In this setup, there is only one single line, serial.begin 9600. This opens the serial monitor at 9600 baud to see ping results. And in void loop, this starts with a delay of 50. That is, it waits for 50 milliseconds before pings, about 20 pings per second. 29 milliseconds should be the shortest delay between the pings. Duration equal to sonar.ping function. That is, the output of sonar.ping is stored in duration variable. And the distance variable stores the distance, which is duration by 2 into 0.0343. This formula is evaluated and the result is stored in distance. Now the next line, serial.print distance equal to, prints the distance equal to on the monitor, and serial.print distance, which is in small. This is nothing but the variable contents. So distance will be 0 when out of set max range. So here this command prints the actual distance on the monitor. Serial.println cm, that is centimeters. So this is the last command which prints centimeters on the monitor, and the program now loops back and a delay of 50 milliseconds is executed. Then the program again continues. This is how the program code works. You can also use distance equal to sonar.ping underscore centimeter function, or distance equal to sonar.ping underscore in function. which returns the measured distance in whole centimeters or inches. With this function, you do not need to take a duration measurement and calculate the distance. Straight away, you can get the distance. Now next comes waterproof JSN-SR04T ultrasonic sensor. The JSN-SR04T is an easy to use waterproof ultrasonic distance sensor with a range of 25 to 450 centimeters. If you are planning to build a water level monitor system, or if you need to take other distance measurements outdoors, then this is the sensor for you. When shopping for this sensor, you might come across the updated version, the JSN-SR04T-2.0. This new version works exactly the same but is rated for 3 to 5 volts instead of 5 volts. However, some users have found issues while using the sensors at a lower voltage, 3 volts. Using a longer trigger pulse of at least 20 microseconds instead of 10 microseconds seems to help you or having faulty readings. That is, if you have faulty readings noted, then increase the trigger pulse to at least 20 microseconds to get the accurate results from this new sensor. About the JSN-SR04T sensor. The sensor comes with a 2.5 meter long cable that connects to a circuit board which controls the sensor and does all the processing of the signal. Note that only the sensor and the cable are waterproof. If you get water onto the circuit board, the sensor might stop working. So, what are the differences between this sensor and the HC-SR04? The main difference, besides it being waterproof, is that this sensor uses only one ultrasonic transducer instead of two. This transducer serves as both the transmitter and the receiver of the ultrasonic sound waves. Ultrasonic timing diagram of this JSN-SR04T waterproof sensor. The formula pulse width microsecond by 58 equals to distance in centimeter, and pulse width microsecond by 148 equal to distance in inches. 10 microsecond TTL pulse to signal path to signal pin, that is to initiate the trigger pulse, and ultrasonic transducer will issue 8 40 kHz pulses which are internal, and echo back pulse width corresponds to distance about 150 microseconds to 25 milliseconds, 38 milliseconds if no obstacle. JSN-SR04T specifications. Operating voltage DC 5 volts, quiescent current 5 milliamperes, operating current 30 milliampere, frequency 40 kHz, measuring range 25 cm to 450 cm, resolution is about 0.5 cm, beam angle less than 50 degrees, working temperature minus 10 to 70 degrees Celsius, storage temperature minus 20 to 80 degrees Celsius, small size, easy to use, low voltage, low power consumption, high accuracy, strong anti-jamming, integrated with wire enclosed waterproof probe, suitable for wet harsh measurement occasions. Quiescent current is nothing but the standby current or the non-operating current, which is very less, that is 5 milliamperes. The connection of the sensor to the circuit board is shown here. On the back side of the circuit board there is a jack wherein the sensor cable gets attached. Connecting JSN-SR04T to Arduino Uno. The wiring diagram shows how to connect the JSN-SR04T sensor to the Arduino. The circuit board of the JSN-SR04T has the same pinouts as that of HC-SR04, so it can be used as one-to-one replacement. That is, keeping the wiring same, the module HC-SR04 can be replaced with JSN-SR04T as the pins are one-to-one compatible. The cable of the sensor is plugged into the connector on the back of the sensor, JSN-SR04T's circuit board. JSN-SR04T connections. Example code for JSN-SR04T with Arduino. The code example use digital pin 2 and 3 for the trigger and echo pin, but of course you can change this to any digital pin you want. Having wired up the sensor to Arduino, it's time to connect the Arduino to the computer and upload the code. The sensor can be used without any Arduino library. This code works for the JSN-SR04T-2.02. Using Arduino IDE, upload the following example code to your Arduino. Arduino example sketch to control a JSN-SR04T ultrasonic distance sensor with Arduino. No library is needed. The first line states define trigger and echo pin. Hash define trigger pin 2 and hash define echo pin 3. Then define variables. Duration is defined as long and distance variable is defined as integer. Now void setup. In this setup, define inputs and outputs. Pin mode is used to define trigger pin as output, and pin mode is used to define echo pin as input. Begin serial communication at a baud rate of 9600 is used with serial.begin 9600. In loop, that is void loop function, clear the trigger pin by setting it low. The command digital write trigger pin low makes the trigger pin to low initially, and a delay of microseconds 5, that is a 5 microsecond delay is given. Later, trigger the sensor by setting the trigger pin high for 10 microseconds. Digital write trigger pin comma high. This makes the trigger pin to high, and the next line delay for 10 microseconds, that is the trigger pin is kept high for 10 microseconds, then immediately the trigger pin is made low. Read the echo pin pulseln function returns the duration, length of the pulse in microseconds. So this pulseln function echo pin will give the output, and this is stored in the duration variable. Next, calculate the distance. The calculation is done using the formula duration into 0.034 by 2. This formula is evaluated and the result is stored in distance variable. Print the distance on the serial monitor using Ctrl plus Shift plus M. This Ctrl plus Shift plus M will take you to the serial monitor to look onto the output. Serial.print distance equal to is printed on the monitor. and serial.print distance. This is the variable distance, that is the content of the variable distance is printed. Serial.println cm, that is the cm is printed at the end, and a delay of 100 is incorporated. This is the loop statements. You should see the following output in the serial monitor. So distance equal to 163 centimeters is shown as an example here. Example code JSN-SR04T with Arduino and New Ping library. The NewPing library can be used with many ultrasonic distance sensors. The code which uses the NewPing library is a lot shorter than the code used before. You can install the library by going to Sketch, Include Library, Add .zip library in the Arduino IDE. A modified example code that can be used with the same wiring setup as before is shown. Arduino example sketch to control JSN-04 SR04T ultrasonic distance sensor with NewPing library and Arduino. Include the library using #include newping.h. Define trigger and echo pin using #define trigger pin 2 and #define echo pin 3. Define maximum distance we want to ping for, that is in centimeters. Maximum sensor distance is rated at 400 to 500 centimeters. So #define maximum underscore distance 400, that is 400 centimeters is the maximum distance we want to keep. NewPing setup of pins and maximum distance. NewPing sonar equal to NewPing trigger pin comma echo pin comma maximum underscore distance. This is to set up the pins and maximum distance. Void setup. Open the serial monitor at 9600 baud rate to see ping results. Serial.begin 9600 will open the serial monitor at 9600 baud rate. Void loop. In this loop function, wait 50 milliseconds between pings, that is with the command delay 50. Measure distance and print to the serial monitor. Serial.print distance equal to send ping get distance in centimeter and print result is with serial.print sonar.ping underscore centimeter function. This will give the result, and the result is printed on the serial monitor. And serial.println cm is the last one which prints centimeters on the serial monitor, and the program goes in the loop. Thanks for watching. Subscribe and like vsrtechinfo.